Hello and welcome to Eaton's Technology Summit for Data Centers and Energy, coming to you from Madrid. I'm Emma Strutton, I'm Head of Channels at DCD, and delighted to be joined today by Adam Gough, who is the Director of Engineering for the EMEA Data Center segment at Eaton. So thanks for joining me, Adam. How are you?
I'm fantastic. How are you, Emma?
I'm very well, thank you for asking. So to start off with, are you able to tell me a bit more about you and your role at Eaton?
So my role in Eaton, I'm the Director of Engineering for Europe, Middle East and Africa. What we take care of is end-to-end systems designs for our customers. We assist our consultants. So what we take is a very holistic approach to how systems are designed and integrated for data center deployments. And that covers power, looking at the IT side of it, the white space, so integrating our products into there, but also now with the acquisition of Boyd Thermal, we're looking at the cooling side of it, CDUs, cooling strategies. So we're building up the team to support that too.
Fantastic, thank you. And to start us off, it's obviously hard to read any industry news article at the moment without the unprecedented demand for compute coming up. So how is this changing the size, the scale, the layout of new data center facilities?
Well, the size and scale of deployments has increased significantly. I mean, we're talking about build-out blocks now that are 12.5 megawatts per powertrain. So if you look at a 6 to make 5 redundancy level, you could have 12.5 megawatts of IT just supported off of that. That is changing rapidly as well as we get increased rack densities. We go from 142 to 240 to 600. What we're seeing now is the size of the white space is contracting, but the cooling architecture and power distribution are growing increasingly bigger.
Yeah, and then facility level, obviously you mentioned there the white space contracting, but what are the most significant power and cooling engineering shifts that you've seen?
Just the sheer density alone.
Yeah.
Sheer density. We see a shift towards as we start to go on to the next chip architectures that are going to be in 27, 28, we're shifting from 415 volt AC to 400 volt DC, 800 volt DC. We're looking at medium volt solid state transformers, 800 volt DC distribution. That dramatically changes the architecture and even the site layouts. So whereas a lot of the original power distribution would have been either containerized or built within a building, the MVSST is designed to be sitting outside. So even that, the space allocation of what's your outside space, what's your inside space, and how that works changes dramatically with the advent of the new power distribution technologies.
And when it comes to the building itself, do you think we are reaching the limits of traditional floor loading, structural design, etc.?
It's getting to a case of I wouldn't say there's any limits on structural design. You could always design bigger, stronger. However, we're getting to the limits of what makes sense to be bigger. So previously, over the years, there would have been raised floors where the cables would have come in underneath it, the equipment would have been supported. As things get heavier and power gets more dense, everyone's moving to top fed. The weight implications and the size of the racks are making the raised floor not make sense anymore. So it's a lot easier and it's a lot cheaper to achieve the same thing by using just a traditional concrete slab with the appropriate weight loading requirements. So neither is going away, but it's which makes the most economic sense to do.
Yeah. And when it comes to choosing where to build, what design and engineering factors are becoming the most critical?
Well, from our perspective, we're more like we build where we're told. So a lot of that's driven by the customers. But if you look at the site acquisition strategies, so like key consideration is power. Power and space availability. Can you get your networking? Can you get water supplies for your cooling? And I know there's a shift going on to obviously less water requirements, and there's dry data centers which like closed loop systems, but all data centers require some water. So the main thing is, can you get a site with power? Everybody's scrambling for power. The delays on grid connections are strangling everybody. So it's not about people deploying in the traditional locations where things would have been happening over the years, like the flap D market. You see things expanding out massively now. There's other markets going up. Frankfurt was the hub for Germany. Now we see a lot going on in Berlin because there's available power in Berlin. There's none left in Frankfurt. You see Zaragoza over in Spain, which is having massive hyperscaler, but also multi-tenant data center developments now as well. And that's all down to availability of power on land. So the availability of solar and wind is driving that massively. And I would say favorable regulatory regimes as well. So that's a big thing as well.
Yeah, absolutely. And when it comes to that kind of future-proofing flexibility, we see tech refresh cycles becoming more and more frequent. Data centers are, meant to stand for 10, 15, 20 years plus. So how much of that flexibility do you think is required in kind of a fast-moving market?
It's massively required, but I wouldn't say not necessarily the flexibility. It's the speed at which we can get a reference design in place to move at speed. So if we sit down with a customer and we do a lot of the design development at very early stages, we standardize as much as possible, where possible, their deployment from a cooling perspective, the power architecture perspective, the white space perspective. You can migrate that across sites. Traditionally, what would have happened before is that every data center would have been fresh sheet of paper, would have designed from scratch. There would have been an 8 to 12 month initial design period. And what we're doing is we're working with our customers, so our clients and our consultants, to shorten that design period. We do it once, and then there's the localization part. So what we're doing is, in order to mitigate the design refresh cycles, which are happening 2-3 years now, and now it's going to be turning into a year, we're shortening the design period so people have certainty on what the supply chain looks like, what your power architecture looks like, what are the factory slots available for manufacturing. So we're able to move at speed. Speed is the thing that's going to change. So if you're going from your traditional 4 to 5 year kind of design and build cycles, the technology would have changed 2-3 times since then. So everybody needs to focus on how can we get the design in place and move for speed of deployment, speed of power on, and tokenization.
Yeah, that makes sense. And looking ahead, whilst I certainly don't expect you to have a crystal ball, do you think AI will standardize builds around certain architectures or push the industry towards greater customization?
There is a move to standardize the architectures, but from my experience, there's a constraint in that, and the constraint is what's available in the market from a supply chain perspective. We've seen some of the reference architectures coming out with equipment that's sized for certain markets that if you start to look at the lead times across the board, while that might be the optimal engineering design, from a speed of deployment perspective, it might not be optimal. So if you're going for gensets that are non-standard design or transformers that are non-standard design, you're increasing lead times. So what we look at with our customers is optimizing the design for their use case, for their customers, but also for the market in which they're deploying as well. So a lot of that is based around individual customer requirements. So from our perspective, all the designs that we do are for the end use case. It's not a case, and I'm a firm believer that while you see reference architectures coming out, it's a good starting point. Nobody can build that because there's too many constraints and too many considerations that haven't been taken into account in that. So it's a good starting point, it's directionality, but it's not an end design.
Yeah. Well, Adam, thank you so much for taking the time to join me, and hope you enjoy the rest of the event. Thank you.
Thank you, Emma.
Thank you.